the other one is about the weak gravitational density effects on the polarization of isotopes of the cosmic microwave background. But before I get into details, let me give you a brief outline. Thank you. Let me give you a brief outline of my presentation. So, firstly, I will attempt to briefly review the thermal history of our universe, in particular the thermal history of the early universe. And afterwards, I will talk about each of my projects in turn. Okay, so on this diagram, you see the paradigm of the history of our universe. So today, in the present, is over here on the right-hand side. And the Big Bang happened about 13.7 billion years ago, over here on the left-hand side. Yes. And ever since, the universe has been continuously expanding. The first stars came about 400 million years after the Big Bang. The first galaxies formed about 1 billion years after the Big Bang. What's more interesting though is what happened during the first tiny fractions of a second immediately after the Big Bang. So this period over here. What's interesting about this period is that the universe underwent a period of very rapid exponential expansion, and it was completely empty of particles. It was completely devoid of particles. And yet it expanded really rapidly. And we call this period of rapid expansion inflation. And we know a great deal about this period and the physics taking place during this period from another object, which is a special type of radiation emitted about 400,000 years after the Big Bang. And we call this radiation cosmic microwave background. And it's depicted here by this bluish greenish arrows. So can you start please? Yeah, so to sum up, the most crucial cosmological epochs in terms of early universe cosmology or inflationary cosmology are the inflation, the rapid expansion of the empty of particles universe, which happened during the first tiny fractions of a second, and then the emission of the cosmic microwave background, which took place about 380 or 400,000 years after the Big Bang. And today we observe this cosmic microwave background, and we measure the imprints of the physics taking place during inflation background. And of course, we don't know what happened exactly at the Big Bang. We don't know that really, unfortunately. Can you start, please? There are yet more unanswered questions. In particular, how did our universe get populated with particles? So this is again a timeline or a log of the evolution of our universe. So time goes in this direction, and but this time we have zoomed in onto the early stages of the evolution of our universe. So the Big Bang is over here, where the yellow question mark is, and today is over here, on the right hand side. Yeah, so as I said, immediately after the Big Bang, the universe inflated. It was completely empty of particles and underwent a period of very rapid expansion. And this took place up until 10 to the minus 32 seconds after the Big Bang. So it's a very, very brief expansion, yet very big. And we know for a fact also that the universe at about 10 or 100 seconds after the Big Bang was populated, or it was filled with very energetic particles such as electrons, protons, neutrons, neon radiation, and alpha radiation, of course, and radiation in photons. So the universe was filled with these energetic particles which were streaming really fast, and they were colliding as well. And the electrons and protons could not bonds. They could not form stable atoms just because they were moving really fast. They were really hot. So the universe, the state of the universe was that of plasma, and the universe was also not transparent at this stage, just because it was filled with electrically charged particles such as electrons and protons, as I already said. So photons used to bounce off electrons and protons, and they basically could not propagate freely. So the universe was in this state from about 10 seconds or 100 seconds after the Big Bang up until 300 or 400,000 years after the Big Bang, when it had, by the time it had expanded significantly, and you know that when something expands, it cools as well. So the particles, if you like, cooled down as well, or they just slowed down. So now when electrons and protons collided, or electrons and nuclei, such as protons and neutrons collided, they could form bound states such as neutral atoms. And therefore, suddenly, at about 300,000 or 400,000 years after the Big Bang, the universe became populated with all these neutral atoms. And it became transparent to radiation as well. So all the radiation, all the photons which were present earlier on, now could propagate freely. And today, about 13 billion years after the Big Bang, we can still observe this radiation. Of course, it has cooled down significantly because the universe has continued to expand since the emission of this radiation. And we observe this radiation as a very cold cosmic microwave background, which is about minus 270 degrees. So it's really cold. But we can still observe it and measure, just because the universe became populated with atoms which did not inhibit the free propagation of radiation ever since. Yes, but what's the interesting question is what happened between the end of inflation and the first 10 seconds after the Big Bang? How did our universe get populated with all these particles? And we call this period reheating, just because during this, it is believed, or we hope that during this period, the inflaton field, or the field which drove the universe to expand, transferred most of its energy to the particles which were overheated. Yes, so can you hear slide, please? So just to sum up, what is inflation? So shortly after the Big Bang, the universe, we believe that the universe undergoes a period of rapid inflation. And during inflation, the universe is completely empty of particles and matter. However, all of its energy budget is stored in the vacuum in the form of a decaying with time and spatially homogeneous inflaton field. So mathematically, we say that when the vacuum is energized, then there must be a spatially homogeneous inflaton field, which basically stores all the energy of the vacuum. Okay? Slide, please. So reheating. As I already said, when inflation ends, reheating starts, and mathematically we say that inflation ends when the inflaton field, or the energy of the vacuum, stops decaying with time and begins to oscillate. It oscillates, of course, very little. And the amplitude of these oscillations is very small, just because the energy of the vacuum has decayed significantly. However, to avoid that the universe ends up empty of particles, the inflaton field, or the vacuum, has to transfer its energy, or most of its energy, into ordinary particles, as I already said, particles that comprise all of us and everything around us. And we call these particles the standard model particles, and they are basically quantum excitations of the standard model fields. And of course, there are other particles in nature, such as dark matter. Of course, we don't know the nature of dark matter but we know that it must have been, the universe must have been populated with dark matter particles as well after inflation. And as I already said, just to emphasize, this process of populating the universe with particles out of the vacuum is called reheating, and basically heralds the start or the beginning of the thermal history of the hot Big Bang or the hot universe. Why hot? Well, because the universe is filled with hot particles, as I already said. Slide, please. Yes, and a few words about the cosmic microwave background, basically the object which gives us all this information about the universe. After reheating, the universe was hot and dense. Matter was in the form of free electrons and nuclei. And by nuclei you mean protons and neutrons. And there was sort of light bouncing between them. And as the universe expanded, the primordial plasma, or basically the electrons and the protons, and the neutrons cooled sufficiently so that the first stable atoms, such as hydrogen, helium, and lithium, formed. And at that moment, light, or essentially photons, started to stream freely. And today, we are able to observe this afterglow, if you wish, of the Big Bang as microwave radiation, and we call it the cosmic microwave background, or the CMB for short. Slide, please. Yes, and just to overview the timeline, inflation happened up until 10 to the minus 32 seconds. We don't know if the universe inflated before 10 to the minus 34 seconds after the Big Bang, just because we don't have such theories which describe so dense objects. Reheating, well, we know that reheating started immediately after inflation, immediately after the end of inflation, but we don't know when exactly the universe got populated with particles. We think that the universe must have ended at least before 10 to the minus 8 seconds, and afterwards there must have been some interactions between all the matter so that it eventually would settle down to the state on which I described here. And the CMB was emitted about 300 or 400 years after the Big Bang. Slide, please. Yes, and now a few words about my first project. It's called Higgs reheating, and essentially what we speculate is that the Higgs field was the infotone field, or all the energy of the universe during inflation was stored in the Higgs field, whose existence is no longer speculation after its discovery 2 years ago. All under concern. We assume that all the energy during inflation, when the universe was completely empty of particles, was stored in the Higgs field, where it was spatially homogeneous, and therefore there weren't any Higgs particles present. Yet there was this spatially homogeneous Higgs field. And afterwards we go about investigating what happens during reheating. How does this Higgs field decays and transfers its energy and essentially populates our universe with all the particles that we are made of. We know that the Higgs field is coupled to all the particles. Essentially, the Higgs field is coupled to us just because we have mass. This is essentially the way we gain mass. This is the Higgs mechanism. So we know that the Higgs field, if the Higgs field was present during inflation, and if it stored all the energy of the universe, then it must have decayed to other particles. So this is a very safe way, if you wish, of approaching reheating. And can you have a slide, please? So what I'm doing in my project is, this tool was supposed to be movie clips. But yes, at my simulations. No, they don't work like this. Sorry about it. So essentially what I'm trying to do is to simulate our universe on a three-dimensional lattice and measure the fields on each lattice point. And here, we were supposed to see basically a slice through my lattice and to see how the fields evolve with time on each lattice point. And essentially what we observe in our simulations is that the Higgs field actually oscillates initially, and but it's spatially homogeneous, and afterwards it becomes spatially homogeneous, and therefore populates the universe with Higgs particles. And here I had also, I was supposed to give you an example of one of the matter fields, essentially, not the matter fields, but what happens with radiation. Initially, you would see that there wasn't any radiation, afterwards the universe was populated with photons. So in our simulations, we do observe reheating, but we need to work on resolution, optimizing color codes, but we think that we're on the right track, and it looks really promising. All this more, basically the assumption that the Higgs field was indeed the inflaton field, and it indeed stored all the computation. And now, please, a few words about my second project, which is about the CMB.
Sorry to interrupt you.
Okay, can you be okay, I'll skip this one. Yeah, I'm really sorry. Just the other slide, please. Yeah, so quickly. We know how to describe the cosmic microwave background really accurate, really precise. And we know that when we look at the microwave background, we essentially look at the distant universe. So when we view the distant universe, when we look at the distant universe, we view it through the intervening matter between us and the distant universe. And we know that this intervening matter has a gravitational field which distorts the path of the CMB photons. And essentially, we can map this matter between us and the distant universe. And this is a map of the dark matter, of the matter that is actually invisible, but we can map it using some clever techniques and the CMB. So this map has been done using the temperature and isotropics of the CMB. In my project, I'm trying to basically reproduce, not reproduce, but make a similar map of the dark matter using the polarization and isotropics of the cosmic microwave background. And hopefully they will agree to some extent. But we hope that the map that we hope to produce will be more accurate and with higher resolution. Yeah, so that's it. Thank you very much.
Okay, thank you very much, Kaloian, and we have just time for one or two very quick questions. Please introduce yourself.
My name is Georgi. I have two questions. The first question is on the Higgs field. Is it something new discovered recently and the work has been done? And does it couple with the model we've seen before of the how the universe starts from the Big Bang, or it's bound with the Einstein theory? And the second question is it's more like about the history and the theory you gave in the beginning. When you say it happens at 10 to the 34 of the degree of the second, how do you measure this in human language, please?
Well,
so inflation comes from 10 to minus 34 degrees second to 10 to minus 32 seconds. Please, could you explain and give us some kind of imagination how we can measure this kind of speed in human language? Yes.
Okay, so
yes, what kind of tests you do to kind of give a realistic?
Okay, so essentially, yeah, I can't explain it really quickly. I'm sorry. But the thing is, we need such inflationary stage just because we observe that the universe is really homogeneous. And the only way that the universe is so homogeneous on large scales is that initially it had inflated. So think of it as a balloon. So initially the balloon could have a lot of inhomogeneities, it could have a lot of defects, but once you inflate it, all these defects smooth out. And of course, we know that this cannot happen for infinitely long. Just because our universe, it might be infinitely big, but still, what we see is finite. And therefore, we deduce that there must have been a period of really rapid expansion going on for about for a really short period of time. So that's the way we estimate. We haven't measured them exactly. We have just estimated the order of magnitude. Yeah. And about the other question about the Higgs field, well, there are many models about many models about the early evolution of the universe. However, most of them involve new exotic fields which we haven't observed in nature. And now we want to model our universe with just the fields that we have observed so far in nature. And that's the reason why we decided to focus on the Higgs equation.
Okay, thank you, Kaloian.
Thank you very much.
Just a couple of minutes probably to stretch our legs and then be back in 2 minutes in your places for the next very interesting session on finance, which is going to be chaired by leading finance expert and very important member of the Bulgarian Society in Oxford, Kaloian Lozanov.